Yeah, hi Rahim, this is your trainer Musab. Okay, so I hope you are doing very well. You are doing good. We'll start a topic. Okay, we have covered the frame header. Yes, what are the fields in it? You know them. We have looked upon some fields: a preamble, an SFD, right? And then the MAC addresses for both destination and source, right? And then we studied the type, then payload, and at last and FCS. Yes, these are the fields that we have studied and we have seen in a destination, MAC address, source address, SFD, preamble, type, okay, payload, FCS. These are the fields that are present in a data link layer header. Now today we will discuss frame switching. Okay, frame switching. Frame switching, in simple words, it means that you are having a frame in your hand and you are just passing it on. Okay, passing it on is what we call a switching. Okay, that is the meaning of switching. Okay, so what we actually do here, let me explain it. When we are saying that we are switching a frame, it means that we have a device, we call it switch. Okay, we call it a switch, and the devices that are connected to this intermediary device, that is different PCs. Yes, now in order to communicate, they should be able to send their data from one PC to another, isn't it? Now that is the data that is going on is what we call switching. Okay, a frame switching, because switch understands a frame, that's why frame switching. We are saying that we have a frame and we are switching it. Alright, also we have studied that the header that we have in the data link layer is called a frame header, and it is also the PDU here, the PDU at data link layer. A frame is a PDU at data link layer. Yes, so it all revolves around frame. Okay, frame switching, frame is a PDU, the switch understands frame, and all these things are going just around the frames. Okay, so it is very important to understand what a frame is and what are the components of the header of this frame. Alright, now from here we will move on and I'll explain how we are actually doing a frame switching. Okay, just allow me a minute. Alright, now let's make a very simple topology here. Let's say this is a switch 1. Okay, there are multiple ports in just one switch, you know that. A switch is a device that has many ports, isn't it? And with these ports there are different devices. Okay, let's make a server here, let's connect a PC here. Okay, let's connect a laptop here, let's connect let's say camera here. Okay, let's connect a mobile phone here, and so on and so on. You can connect many devices with a switch. Okay, meanwhile we cannot just directly connect the mobile here. I'm just taking it for an example. You will connect first an access point here, which will give you the availability to have your device, your mobile wireless connection with this access point. We have studied access point. Yes, I hope you remember that. Now from there let's move on. Whenever we send some kind of data or some kind of request, we actually are sending up a frame, basically a frame at the switch layer from one PC to another. Okay, now before that, before even this communication is happening, switch does some functions here. What are those functions? The first thing it does is it builds and maintain a MAC address table. Okay, you know, each and every device has a MAC address and it is connected to just one single interface of a switch, isn't it? Now whenever any kind of data is entered into that port, the switch will learn that this device, this PC here, has sent the data obviously, and this device is connected to this particular interface or port. Now that learning is called that learning is stored in the CAM table. This, you know, MAC address table is stored in CAM table. CAM. What is CAM? It is content addressable memory. Okay, CAM. So it is the same thing that you have an operating system installed in a hard drive, isn't it? So hard drive here is the content addressable memory and the MAC address is the operating system, for example. Okay, so that MAC address is then stored in the CAM table. How that MAC address table looks like? It looks something like this. Let me take another example here. Example color. Okay, I'll make a table here just like this. Okay, let's make port here and let's make MAC address here. Okay, let's say that PC1 is connected with this interface, this MAC address, right? What we will do is we will name that interface 0/1. Okay, 0/1. So let's make that interface 0/2. Let's make this 0/3, 0/4, 0/5. Alright, now after naming this, I'm going to make a table that the switch makes. Okay, let me take another color here for the better understanding. Whenever switch receives any kind of packet or frame from this PC, it will be entered in 0/1, right? The PC will send this any kind of packet to 0/1, this interface. As soon as it enters the switch, 0/1 got registered here. Okay, a MAC address of this PC has been put here. Let's take an example here as AAAA for simplicity. Okay, so this is the table here. That's how it looks like. Again, when switch 1 is going to send this server any kind of data, or other PCs or any other devices some kind of data that this PC send, in that scenario the devices that are connected, let's say this PC is sending some data to server. When the server is going to respond, then in that case the data of the server will be received at 0/2. Yes, 0/2. And at this point switch 1 will be able to understand, or will be able to store the MAC address of server in that interface, which means let's take an example of BB. Okay, so again a MAC address table has been initiated here. The first MAC address was from 0/1 in this PC, that is AAAA, and when any kind of data is received from any device, let's say server here, then in that case the MAC address and the port number will be used and will be stored in the MAC address table, right? So for the simplicity, if you just don't want to forget it, then we should actually write this thing, isn't it? I'm gonna write this here. What is the switching procedure? Okay, let's do one thing. Let's erase this part. Okay, let's erase this part. You can go back and just have a look at it, what I have written, and make your notes. I hope you are making notes. Yes, if you are doing that, that's great. If you are not, I highly recommend you to start doing it, because at some point you will start forgetting the things that we are studying. Okay, if you are doing that, that's great. So we are studying now the switching procedure here. Okay, whenever a switch receives a frame from PCA, yes, this the most important thing, and the very first thing that it does is switch enters the MAC address and port from where it was entered, and port from where it was entered, right? That's what I have done here, what I have demonstrated here. The MAC address, that is this part, and the port number, that is this part, will be entered or will be used for populating the MAC address table. The third thing the switch is going to do is, if it has already learned the MAC addresses and the interfaces, then it will forward that packet or that frame directly to that interface. For example, let's assume that this table was already there in the switch part. Okay, in the switch has already learned these two MAC addresses, and it has also learned that these are the interface that are being used at the moment, right? So what switch 1 will directly receive the packet from this PC at this interface, and it will directly forward to the server. Meanwhile, if the switch hasn't learned these two things, these two MAC addresses and these two ports, what switch will do? It will flood the packet. So there are two main terms here. The first is flooding, okay, the second thing is filtering. Flooding means or it happens when you send the frame to everyone, or to all active ports. All those ports that are active, that are connected to some end devices, will receive the frame. Okay, let me demonstrate it here. Let's say we have PC here. Okay, this is going to send a request to server, but if switch 1 does not have any MAC address table, in that case switch 1, after receiving the packet or the frame from PC, it will forward from here to here also, okay, from here to here also, from here to here also, right? Or if there are any other active ports, then it will be forwarded to those ports also, right? That is called flooding. Flooding means to flood whatever you have to other ports except that one port where you have received it. Okay, you will not flood any kind of frame or any kind of packet to the port that is already giving you that information. Okay, the second thing the switch can do is filtering. It can filter the MAC addresses or the CAM tables that we have in a table. Okay, and it is basically done to drop the packet, or the frame here. Okay, now these two terms are here, flooding and filtering. Alright, whenever a switch enters the MAC address and the port from where it was entered, it will populate the MAC address table. If it does not have any kind of MAC address table, it will flood the MAC address, it will flood the entire frame also to other ports, and will find out who has the destination MAC address. Okay, in this case, if PC does not know the server's MAC address and switch 1 also does not know what devices are connected to its ports, then it will flood every kind of packet of frame that it is receiving on this interface or any other interface. Alright, if it has not learned any kind of MAC addresses in that time. If switch has learned some kind of MAC addressing, or it has populated the MAC address table with its ports, then in that case it will directly forward to your destination. Okay, so the third step it will do is it will switch will it's going to check the table for destination address. Okay, if we don't have any kind of destination address, then the switch is going to flood the frame. If it has the destination MAC address, just in this case it is going to directly forward this frame to this interface, one interface. Okay, now coming to the fourth point, destination with matching MAC address. MAC address replies. Okay, destination with matching MAC address will respond to the packet here. So let's say server is the destination here, and server will respond with its MAC address to the switch. Alright, after that switch is going to learn the destination's MAC address. And it will populate MAC address table. Populate MAC address table. Alright, these are the 5 points here. Now there are some more, so I will write it up here. Just I hope you have written them. Okay, now the last 2 points are, after learning the destination's MAC address, the switch will learn, the switch will forward the frame. After that, no flooding for destination finding will be done. Now, although there are many scenarios where a packet can be flooded, but not for finding out this destination MAC address here. Okay, alright, so that's how the frame switching is working here. Because switch works with a very high speed, in that way it will learn the MAC addresses very quickly. Also, after learning this, we do not want the memory of the MAC address to be fulfilled by at a moment, right? So what we used to do is, we actually have a timer here, and we call it aging time. This time is used to keep track of MAC address table. Okay, keep track of MAC address tables. Now these MAC addresses are there for a certain time, and that time is 300 seconds. Okay, 300 seconds. If within 300 seconds these devices are able to communicate with each other, then it will be resetted. So you will write that there are two cases here. Okay, in 300 seconds it will either reset it. Okay, if in the scenario where you have got the communication happens. Okay, and if you have already got the 300 seconds, then it will be flushed or deleted from the MAC address table, because of the reason that there was no communication. So after a certain period of time, whatever we can configure that 300 seconds or 500 or whatever seconds you want. Based on that, the frame or the packet will be resetted. The timing of that packet or frame will be resetted, or that packet will be flushed out. Okay, it will not move forward from there. Alright, okay then. Alright, now if you have understood this whole frame switching, I want you to download a tool. I'm going to erase it. A tool that we call Cisco Packet Tracer. You will go to a website that is Skill for All. Okay, you will register there. After that, you will download the Cisco Packet Tracer. Okay, and after downloading that packet, you will be start doing your practicals. Okay, how will you do that? What will the practicals are that I'm going to guide you through. I'm here for that, but in case you need any help, then you can ask me. Although you have to download this software, it is very helpful to understand the concept and the functions of different devices, and also the functioning or the working of a network. Okay, what are the messages that are received or sent in a network? All those topics or all those concepts will be very much clear from this single single software. Okay, all right, now let's have a look at data link layer. We have covered that. Okay, we will be looking upon some types of applications or communications, and they are types of communications. Okay, these type of communications are divided in 3 categories, and that is unicast, broadcast, and multicast. Okay, a unicast is a kind of communication where you are just focusing on one-to-one communication. So let's say something like this is a topology here. Okay, now one wants to communicate with 3. One wants to communicate with 3 here, right? That is a kind of communication we are seeing. Unicast means just one-to-one communication. Meanwhile, in the broadcast communication, what we usually have is devices. You must have heard of the radio broadcast. Yes, 1, 2, 3 and 4. All the devices that are connected with any one node of the device. Okay, let's say this PC1 is connected with PC1, 2, 3 and 4. Okay, so if a PC sends any kind of data, it will be broadcasted, means it will be received by each and every device here. Okay, each and every device will be able to hear it, and we will be able to respond to it also if we have allowed that much of configuration here. But again it will consume the most of the bandwidth of a network, and it will not allow other communications to happen, okay, in broadcast. Meanwhile, in multicast, you actually have devices. I'm going to take the same topology here, okay. You have got the devices, okay, and if device 1 wants to communicate with just 3 and 4 number of devices, okay. If we want to communicate with just 3 and 4, we'll put it in a group, okay, group. And if this PC is sending the device for just these two PCs, not with number 2 and just for number 3 and 4, then this kind of communication is called a multicast communication, where we are joined in a group, or we are the part of a group, we are the admin of a group, and we just forward any kind of message, and it is received by just those people who are in that group, right? This is the same thing as you see in the multicast, in a group of a WhatsApp, where you have a group, there is an admin, and whatever the admin is sending, it will be received by each and everyone, right? Okay, then, so these are the basic kind of communications that we see in a LAN. Now we are going to study the header of layer 3, okay. Again, I'm going to make a picture here. Like this. Layer 3, layer 2. We have studied the frame here, right? Frame header. This is the part we are done with. Now we will study internet or network layer header. Internet layer header, okay. That's what we are seeing here. L3, L2, and L3 is nothing but the link, the network layer with internet layer. Alright. Now this is called the IP header. IP is a protocol that stands for internet protocol, okay. This internet protocol is in different versions. It has version anywhere from 1 to 15, okay, somewhere 15 here, maybe 12 or 15, it is between them, but our main focus is on just two IPs, IP version 4 and IP version 6, okay. IP version 4 and IP version 6. Alright, that is those two very important protocol versions that we use in a communication network. Alright, if there are although there are like many other versions here, but we are going to study 1 and 15. Why? Because all those other versions either were not successful, they were not able to go beyond scope, they were not able to make it in the market, but IP version 4 and IP version 6 are still working in the network, and they have their own significance. Now first we will be studying this IP version 4 header, okay. Each and every protocol has its own header. In the same way, IP version 4 has its own header. Alright, I will start with the very first field. These are the fields that I have already told you about in the header or frame header, right? IP header frame, IP header. Now the first thing that you will see in an IP header is the header size, okay, version. The version, this version will be written in 4 bits, okay. I have already talked about these bits here. So let's say 0 0 1 0. What will be the value of these bits? It's going to be 2, right? Because we know 1 2 4 8. In this way we will be able to identify that making this bit on, we are actually saying that the value of these 4 bits is 2. Let's make it 0 1 0 0. What going to be the value of this 0 1 0 0 bit? That is 4, right? That is the same thing that we see at this version here. Okay, there is no difference between these. Now coming to next header. In the next header we talk about header length. Okay, what is the total length of the header? Now the length of the header can range anywhere from let's say 20 bytes to 60 bytes. Remember, we are talking in bits here, and we are specifying that the whole header is in 20 bytes at least. So 20 bytes is the minimum value and 60 bytes is the maximum value. I will explain it why it is so, but as of now you will understand that there can be minimum of 20 bytes of an IP header and a 60 maximum value of an IP header. Okay, now in the header length, the header length by itself is of again 4 bits. Okay, these 4 bits can be represented in hexadecimal anywhere from 5 to 15. Now we actually have to multiply it by 4 in order to get the answer. Alright, that is why we are saying that our header is actually anywhere from 20 to 60 bytes. Okay, whenever you multiply the value of these 4 bits, because we know that the minimum it can go, 4 bits can make a minimum of 0, right, and a maximum of 15. We know that. I have already told you 8 plus 4 plus 2 plus 1 is equals to 15. Okay, these are the 4 bits that we are using. Now so if you multiply the number, you will get the exact the length of the header here. Okay, again we are not done here. We will move on with our next field. There are many fields in the IP header, and the next of them is type of service. TOS field. Okay, this is used to prioritize. Now this is 8 bits and it is used to prioritize the data. Okay, this is the TOS field type of service where you prioritize any kind of data. So let's say you are actually saying that we have to work on the VLAN part or the voice applications, so you want the voice data to go first. In that case you will prioritize the voice data. Okay, and then when it is received on any kind of router, then it will look at the TOS field, and in the TOS field, when it is going to find out that the voice data is at the topmost priority, then it will send the voice data first, and will be able to either congest or just compress all other transfers that are going on, so it will allow the maximum bandwidth that it can use. Okay, this is the type of service field here. After that comes the next field, and that is total length. Let me write that down here. Total length. Okay, alright, these are the 4 fields here first. Now the total length identifies the length of it identifies length of data plus header. Okay, so here we are basically saying that we are also telling you about the data, what is the size of data and what is the size of header. Okay, so that is going to make up as the total length here. Alright, after that I will say that 16 bits the total number of bits here in the total length. Okay, now moving on with different next fields are in front of us like this. I'm going to make it a single thing because whole this field, this row here is used for fragmentation. Okay, what is fragmentation? Fragmentation is nothing but you identify that there is a receiver here. Okay, there is a receiver somewhere and there is a sender. Let's say that this sender is a server, okay, and this receiver is a PC, or for more assumption, let's say it's a mobile. Okay, now server is more capable than a mobile, isn't it? Server has more energy, server has more RAM, more kind of speed, but mobile is not capable of that much of things. Yes, so if this mobile is going to make some request to the server will send much of data immediately, right? Because of the speed, high speed. Okay, because of this high speed the data will be sent automatic. But will the mobile receive it immediately? No, it will not be able to do so because the configuration of a mobile is very much low than the other devices or other things here in the network. Okay, so in that case we want to know that what is the capacity of mobile to receive any kind of data, any amount of data. What is the amount that is unacceptable for mobile? For that we allow something we call MTU, that is maximum transmission unit. Okay, maximum transmission unit. This maximum transmission unit will be the thing that will allow us to fragment any kind of data. So let's say the device is saying that I can receive 1500 of byte at a time, but the sending side is saying that I will be sending 10 GBs of data at a time. Okay, so what's going to happen is the sender will negotiate with the receiver, and the receiver will say that I cannot accept 10 GB of data at a time, so you need to fragment it. Okay, you need to break it down into smaller steps so that I can receive it. In that case the destination will come to know that yes, we cannot send that much of data at a time, so we have to make it we have to fragment it, we have to make it in chunks. Now to make that thing happen, we say that these 1500 bytes will be sending at a time, and that 1500 bytes is called the MTU. Yes, now let's say there was a packet of 10 GB. Okay, there was a packet of 10 GB and that got fragmented in 3 or 4 parts. Okay, just for example here, 3 or 4 parts. This whole packet is a one entity. Yes, so it will tag this as 1, that it belongs to 1. Now IP is a connectionless protocol. IP is a connectionless protocol. Okay, connectionless protocol is a protocol that does not have any guarantee that it will be able to receive, or it will be able to definitely send your data, or it has no guarantee that the sender will get an acknowledgement of the receiving of the packet. It has no guarantee that the receiver is going to receive the data no matter what. Okay, there is no guarantee that your data will be dropped and it will not be able to reach the destination, in this case mobile. Okay, so for that we have to make it in this kind of sections here. Now since there are chunks, each chunk will be going to through the path independently, so in that case they should also be identified by another number. I'm just taking these as an example here. You will get to know what I'm talking about when we will going to be do when we are going to do our labs, right? So 1A, 1B, 1C, 1D. Now each and every packet hai, each and every packet will be able to just go with the flow, and when it has received on the destination, let's say mobile will be able to receive it, and not just receive it, mobile will be able to rearrange it and resequence whatever the packet is sending. So let's say it got received at the destination side at something like this thing 1C, 1D, 1A, 1B. Okay, so mobile will understand us that okay, C should not be here, A should be there, right? So it will replace the A from C and C will be here. Okay, B should not be there, it should be here, so it will replace the B with D. Alright, so there are these very basic things that you just understood. If there are any questions, you can just let me know. Okay, after that yes, we are here. Identification, flag, fragment offset. Okay, these are called the flags, and these is identification. Okay, now in the identification field we are actually specifying this number 1 here. Okay, nothing else. We specify the ID of a packet and we do it in 16 bits. So the value or the length of these identification flags is identification is 16 bits. After that comes the flag, which are around 3 bits. These 3 bits are something like this. First bit is reserved, that is 0, so no one can use it. Okay, the second bit can be either 0 or 1 because it depends on the don't fragment factor. They don't fragment. If don't fragment is 1, it means that we are agreeing on this statement that don't fragment. Okay, there will be no fragmentation. So from here to here there will be no fragmentation. Alright, if this statement is 0, then in that case we are actually denying this statement that don't fragment is wrong. We are actually fragmenting things, so we are fragmenting just like this. Okay, after that comes the more fragment flag, more fragment, and in the more fragment, if it is 1, it means that more fragments are coming. If it is not 1, it is 0, then it means that no fragments are coming. Okay, now this is good because let's say 1C and 1D got received and A is not received. Okay, so if 1D got received and it has this bit on more fragment, okay, then in that case it means that the mobile phone needs to be on hold, or it needs to wait some time before it receives the next packet. Okay, that is the meaning of the statement, a good statement here. Alright, these are the 3 fields here. After that comes the 13-bit fragment offset. Alright, this is also used to identify that A is first, B is second, C is third, D is fourth. Okay, so we have 3 fields: identification, flag, fragment offset. Identification is just used to identify the whole packet identity, and meanwhile fragment offset is used to identify the fragments of that whole fragment of that whole packet or that whole device. Okay, flags are used to notify the destination that don't fragment, which means that we have no fragmented packets. So in that case, if it is 1, that means that we are actually taking those cylinders or all these things, right? Okay, Then let's move on to the next topic here, or the next fields. Okay, and those are this. We have a destination IP and then the source IP. Okay, the destination IP is used to identify any destination, and the source is used to identify any source IP address. Now, even if we talk about this, there is another field here that is important to know. You should note that, although it is not something people normally talk about, but if you are studying the fundamentals, very fundamental, then this is good. You should know about it. Okay, I'm going to explain it here, and that is this middle field here. Okay, there are some fields here also, and those are first time to live. Okay, that is the first field. Time to live field is a field which we use to identify that our packets are not, which we use to make sure that our packets are not being looped in just one network. Let's say a device sends a broadcast message and it never received or it never got any destination, so it will start looping from one device to another, and at a certain point it will get back to that one router. Yes, now this loop is very dangerous, because it will make the network congested, because there are many loops and all these things going on here. That's why we will use this field time to live. Okay, it is basically about a very small field here. Okay, that is of just 8 bits. These 8 bits specify a number. In Cisco devices, that number is 255, excuse me. In Windows you will see it 128, in Linux you will see it 64, and on and on. Okay, there are different types of TTLs for different operating systems. Alright, so time to live for Cisco devices is 255 for Cisco devices, which means that after 255 routers, after crossing 255 routers, the packet that you are sending will be dropped. It will be dropped after 255. Okay, so a packet generated from PC will have a value, let's say 255. It will be then sent to this router, where upon exiting the value will be 254. So at this router it will be 254, on exiting it will be 253. Okay, upon receiving this it will be 252, and on exiting this it will be 251. Sorry, here 2 and this is here 2. Okay, so that is how the value will get decremented, and if at any point the destination is not reachable or it is not present there, then you will get an error that the host is not reachable or the request is timed out. Okay, something like that. But it is because of this TTL field which actually got dropped, or which was not fulfilled because of the looping. Okay, because there was no any other route in the network. After that is the protocol. A protocol is a field that specifies the protocol that is being used at the upper layer. Now after on the upper layer we have transport layer, yes, and below of it is data link. So the transport layer is very important here, because it also uses the protocols, for example TCP or UDP. These two protocols are very very famous, and I can just choose any one of them based on the application that I'm using, and that will be specified in the protocol, which protocol I'm using at the upper layer, so that the destination should be prepared in order to receive that particular that particular header or information that I am storing behind myself, right? After that comes the header checksum. Okay, this header checksum is used to error detect any errors on the header only, just the header. Now we have looked upon the checksum at the data link layer also, but that checksum is detecting any kind of error in the whole packet or whole header also. Meanwhile, the checksum at other layers, we will be discussing a checksum at the transport layer also. So when we are discussing a checksum at a particular layer, then that checksum is actually just identifying or just detecting errors at the layer, not in the data. Okay, so the other field, the FCS, frame check sequence, is something that we study in the frame header, and that is used to error detect any kind of errors on the whole header or frame. Okay, here we will just deal with the errors in the header. Alright, this protocol, by the way, is of 8 bits. Okay, and this is of 16 bits. Alright, now if you pay some attention here, then I've listed all these in a particular way. Okay, and I'm going to explain it why I have done that, because if you add on these 4 bits, which means 8, here 8 which means 16, and here 16 means 32 bits. Okay, again identification flags and 13 bits here, so this is 3 bits here and 16 bits here. You will add it up, 13 plus 3 is 16, 16 plus 16 is 32 bits, isn't it? Same as the upper row. After here 8 16 plus 16 is 32. Now we have studied the IP addresses. We know that there are 2 bits in the IP address, right? So there are 2 bits, 32 bits here. All these on adding up all these bits, number of bits, you will get 40 bytes. 32 plus 32 plus 32 plus 32. Okay, we will take it for 20 bytes. Okay, and that I told you is the minimum length of any header that we see at the IP layer. Okay, any questions till now you can ask. Alright, those 60 bytes are the different fields that we add beyond this. So there are optional fields also. Okay, optional fields. So you have got the options here that can be anywhere from 0 to 40 bytes. Now till here, this is the very dividing line here. Okay, 20 bytes are mandatory to be in a header. If you want to add something more, let's say you want to take some specific path, let's say you don't want to take a specific path and many other things, so in that case, let's say you want to identify or authenticate any destination, in those scenarios you will add some options here. Okay, those options will be carried upon one by one to the routers, and they will be identifying it, and they will be acting accordingly. Okay, so it can be maximum of 40 bytes, 0 to 40 bytes. Now adding these 20 to 40 bytes, you will get again 60 bytes that I told you earlier, bytes. Okay, this was all about the header. If you have any questions regarding any of these, then you can ask at any time in the group also. Okay, you can also ask about any kind of doubts here. If you want to add something, you can do that. Obviously, that's it for today. I'll send you the video here. Okay, bye.